series. Then what all things you can measure? You can measure concentration, you can measure the equilibrium constant, and so on and so forth. You can perform some titrations of redox species. You can perform
What on
certain.
last one?
Yes, someone has.
What last slide?
I'm not able
What
to get
last
your
slide?
question. Your voice is not clear. Yes. What is the question?
Up to galvanic series on behavior series
Ma'am,
only.
we discuss up to galvanic series.
We have discussed up to galvanic series only. Okay.
Yes,
So
ma'am.
what is galvanic series? Galvanic series is the values of oxidation potential arranged in a manner of like the oxidation potential is decreasing from top to bottom, right? Decreasing order of activity. Okay, and this oxidation potential is measured with respect to saturated calomel electrode, and that too when it is dipped in or placed immersed in seawater. Whereas your ECE series is arrangement of the reduction potentials measured with respect to standard hydrogen electrode, and they are placed in their own salt solution of 1 molar concentration, and it is arranged in the increasing reduction potential order from top to bottom. So that is an electrochemical series. The electrochemical series is a very important and has wide application. All electrochemists, people who are working on electroanalytical methods and other things will be using the basic knowledge of this EC series, because these are the standard values. No matter where, in which part of world, what all metal you are using, you will get the same values. Now here what we see, this is used by the metallurgy people more, who are studying the corrosion characteristics, corrosion tendencies of various metals and alloys. So this is more useful to those who are working in a specific area. But electrochemistry people, all electrochemistry people, not only electrochemistry, your electronics and electrical engineering students, people also need the knowledge of these electrochemical series, because when you are preparing certain chips and devices, you should be knowing the redox potentials of these. Okay, so that is the galvanic series. Now, coming to the EMF measurement. Now, according to Gibbs-Helmholtz, what is seen for a reversible cell, the EMF originates from the free energy of the reactions occurring in the cell. So, when n number of electrons are liberated at an electrode or are taken up, okay, so whether it is liberation means oxidation, and take up means reduction. So then N Faraday, that is N into F, of electricity is generated in the complete cell reaction. So we know that at one particular electrode, when electrons are when the metal goes into solution, the electrons will run and the electricity will be generated. So if EMF of this so if E is the EMF of the cell, then the electrical energy produced by the cell is NFE. So minus delta G is equal to NFE under non-standard condition. Now under standard condition, delta G naught will be equal to minus NFE naught. E naught we know that it is when it is placed in its own salt solution of 1 molar concentration. Okay, so we can relate the delta G equal to delta G naught plus RT, natural log of quotient, reaction quotient Q. So minus NFE is equal to minus NFE naught plus RT ln Q. So therefore you can write E is equal to E naught minus 2.303 by NF log to the base 10, 2.303 you have written here. So it is the log of quotient, reaction quotient. So at equilibrium, the reaction quotient Q is equal to concentration of Mn plus by Mn plus, which is equal to Ke. That is your metal ion concentrations. Okay, so that is KEQ. So E naught cell becomes 2.303 RT by NF log KEQ. So when delta G is 0, free energy is 0, change in free energy is 0. your E is 0, and therefore log EQ, that is log of equilibrium constant, is equal to N E naught by 0.0591. Now, for a reaction occurring in the way that is A plus B giving you C plus D, then your E is equal to E naught minus 2.303 RT by NF log concentration of C raised to C, concentration of D raised to D, because these are the products. So product by the reactant that we know. Now this is the half cell reaction. The full E cell will be E half plus E half. One is anode, one is cathode. So this is how they are correlated. E naught cell, delta G naught, and equilibrium constant K. Okay. So we find that E naught cell is equal to RT by NF ln K, and delta G naught is equal to minus NF E naught cell, and um, delta G naught is equal to minus RT ln K. Okay. So it was Nernst who correlated the EMF of the cell with the concentration of your analyte solution or the electrolyte solution. So if you write a reaction for a metal cation which undergoes reduction in this fashion, that is n plus n number of electrons, then you get metal solid deposited on the surface. Now, why for all, whether it is zinc or silver or copper, it is written in this fashion? Because in Nernst equation, we write it in the like the reduction reaction. So what all is your reduced form, that is written here, and this is the oxidized form concentration written here. So your M and E EMF of this particular cell will be equal to E naught minus RT by NF ln reduced form by the oxidized form, which is then written as E of this half cell equal to E naught of this half cell minus 2.303 RT by NF log of 1 by. Now reduced form, since it is the elemental solid metal, it is considered to be 1, the concentration, and the metal ion concentration is written here. So similarly, you are having like um, this we will see later. So for a Daniel cell, if you are having copper and zinc, simplest cell I have taken, like the example is cited. So your this is the EMF of complete cell, like when you connect two half cell. So one half cell will be E naught minus 2.303 RT by NF log 1 by Cu 2 plus ion concentration. Now this is the copper or the reduction half cell. Now although this is the oxidation half cell, still you write here 1 by zinc ion concentration. Now when you are writing it in the reduced reduction form, this particular reaction, you have to take care that all the sign, this is also negative, this is also negative, and this is also negative. Then you write 1 by Zn2 plus. Although oxidation is taking place here, the product will be Zn2 plus, but you have to write the reaction in the same way, Zn2 plus plus 2 electrons giving you Zn solid. So Zn solid will be 1 here, and zinc ion concentration will come here. Now the moment you take it above, or this you put it above, this becomes positive. So you can rearrange later, like negative can be positive, then positive can be negative, depending upon where you are writing these two, because you may write the same equation as if E cell is equal to your E naught of copper minus the E naught of your zinc, this value. Okay, because this is from the literature, and this is minus 0.0591. This part is already calculated because R is the gas constant. Okay, that is 8.314 joules per Kelvin per mole, and T is the absolute temperature in Kelvin. N is the number of electrons in half cell reaction, and F is the Faraday constant 96485, or generally it is taken as 96500 coulombs per mole of electron. Okay, so what has done? E naught of the two are taken aside, and the rest of the reaction is written as minus 0.0591 by N log of, now you see zinc ion concentration by copper ion concentration. Here you have to see that the sign is negative. Then you go on writing as per your convenience, because you are used to write the Nernst equation as per your 12th standard. आपकी कोचिंग क्लास में जो पढ़ाया है आप उसी हिसाब से लिखेंगे. So No issue. Either you write separately or you club it and directly write it. Only thing, when you are solving numerical, keep in mind that any value which you are writing, final value, should be shown that how you are arriving to this value. The formula at least should be there. Okay. Now, this is what, this is a Daniel cell. Now, in this Daniel cell, now we had already seen that your zinc potential is minus 0.76, and for copper it is plus 0.34. Earlier we had seen yesterday. So your E cell value comes out to be cathode minus anode potential, and this becomes 1.102 volt. So Daniel cell will provide you a potential of 1.102 volt. Okay. So coming to the equilibrium constant. Now I think equilibrium constant we had already discussed. So if the circuit in Daniel cell is closed, then the reaction, this type of reaction takes place, and we see that there will be deflection in the voltmeter. So after some time, there is no change in the concentration of copper and zinc. So when the equilibrium is attained, so and at the same time, voltmeter gives zero reading. So when it will give zero reading, when the potentials of both the things are almost constant, same, equal. So this indicates attainment of equilibrium, and in this situation, the Nernst equation may be written as this is your Nernst equation, where you write zinc ion concentration by copper ion concentration as the equilibrium constant K. So at T equal to 298 Kelvin, the above equation can be written as E naught cell equal to 0.0591 by 2, because two electrons are taking part in each half reaction, log KEQ. E naught cell, we know 1.10 volts was read here in the previous slide. So that value is written here. So log KEQ will be equal to, like you just substitute, you get 37.225. Therefore, like take the anti-log of this, K will be equal to 1.68 into 10 to the power 37 at 398 Kelvin. So this is the equilibrium constant for simple Daniel cell. Then we saw a standard hydrogen electrode. The other reference electrodes are saturated KCl calomel electrode, or you may be having 1 molar KCl calomel electrode also. So for a KCl saturated cell, the half cell is represented as platinum Hg2Cl2. This is just like the uh, separation. Then a double line is a salt bridge. So when you have two parallel lines, it indicates a salt bridge or the Frit connection. So the reaction that takes place is Hg2Cl2 solid plus 2 electrons. It gives twice Hg liquid plus twice Cl minus, and the potential obtained is 0.242 volts. So this potential will not change no matter what all reaction is happening in your other half cell. Okay, and that is why it is termed as reference electrode. So the electrode is having two concentric tubes, glass tubes. In the inner concentric tube, there will be a platinum wire, and a paste of Hg, Hg2Cl2 and KCl will be stuffed into it. Here will be some glass wool or asbestos, and outside in this tube there will be a hole here. You can see this cork can be removed and a saturated KCl solution can be added here. So what happens here, some crystals of KCl will be there, and this whole saturated KCl, here you have a ceramic frit. So frit is something like a salt bridge. So you can simply put this AG, you this particular calomel electrode into your uh, directly into your uh, beaker in which your analyte solution is taken, which you want to measure for. Okay, and then the indicator electrode will be there. So one indicator electrode, one reference electrode. So the potential of indicator electrode will be measured. Then AG, the other electrode is AgCl electrode. That is silver wire coated with silver chloride. It is dipped in some HCl containing some quantity of silver nitrate so that it gets saturated with AgCl. So this is a chloride aqueous AgCl, Ag solid. So AgCl plus an electron, it gives Ag solid plus chloride ion. aqueous. So this electrode, the potential of this electrode is 0.199 volt, and the diagram for this uh, silver chloride reference electrode is you have a silver wire coated with silver chloride, and you will be having a solution of HCl inside with a little quantity of silver nitrate into it, so that AgCl will precipitate into this, or it is saturated with AgCl. Okay. Now, the next and the most important part, the very first one, the electrochemical series was made using standard hydrogen electrode. Now, standard hydrogen electrode uses hydrogen, which is an explosive gas. So, instead of hydrogen maintaining at 1 atmosphere, then a simpler electrodes were designed, and all our electrochemistry labs are using either calogal electrode or silver chloride electrode. So they are the reference electrode. No matter with which you are coupling it, the potential of these electrodes will not change. Okay. Now coming to a cell. Now what is a cell? Cell is a combination of two electrodes, um, which is either producing electricity or using electricity for obtaining certain product to carry out an electrochemical reaction. So when you are applying certain electrical current to get a product, it is termed as electrolytic cell. In an electrolytic cell, you have a battery whose negative terminal is connected to one electrode and the positive terminal is connected to another. The small portion represents the negative part. So the electrode to which you connect the negative terminal becomes cathode, and the electrode to which you connect the positive terminal becomes the anode. And you place it into an electrolyte solution. What you will see is, depending on the quantity of current is applied or potential difference applied across these two, there will be deposition of like the migration of ions, that is, anions will migrate towards the anode and the cations will migrate towards the cathode. So, in this particular thing, you will find that the positive ions are accumulated here. So, the metal, if it is a metal salt solution, the metal deposits on the cathode and the weight of the cathode will increase. And you will find that the anions will be accumulated here, and mostly it is seen that it may lead to formation. If acid is there, then first of all H2 gas may form, or then Cl2 and other things may be forming across this anode region. So that is an electrolytic cell. Now in electrolytic cell, the negative terminal is the cathode, whereas the other type of cell is galvanic cell or electrochemical cell. Now in electrochemical cell, you don't have to apply a potential difference or current. You get you have to just connect two half cell by a wire, and in between you keep your voltmeter to measure whether there is flow of electricity or not. In such condition, what is seen, the cathode has a positive charge and the anode has the negative charge. The sign conventions are different. So here the anode is negative because the anode goes into the solution retaining the electrons. So this is the electrode which is very much rich in electrons, and these electrons move in this direction, and because they are moving in this direction, electricity is said to move in this direction, opposite direction. So your cathode will be always positively, or the sign convention for this is positive. So that is a galvanic cell, and it operates, it's a spontaneous, or it operates on its own because of the difference in the, like this is copper and this is zinc. So because there is in the electrochemical series, we can see that the potential E naught values are different, and if you connect two metals which has two different E naught values, then depending on the difference between the magnitude of the difference, if it is more reaction, if the magnitude of the difference of E naught value is less, then lesser chemical reaction will take place. Things are clear? Now coming to the electrochemical cell. uh, the electrochemical cell are classified as uh, different type of concentration cells. Now, due to difference in the concentration, there may be formation of a concentration cell. Now, the concentration cells are classified as electrode concentration cell, and other type is electrolyte concentration cell. Now, electrode concentration cell are, one is gas concentration cell, where you have different pressure of gas, so that it becomes the electrode, because the electrolyte is same here, but here it is 1 bar and here it is 2 bar. Okay, the pressure is 2 bar. So the moment you have like the same HCl solution is there, but the hydrogen gas pressure is different, a gas concentration cell is formed. Okay, then another type of electrode concentration cell is amalgam cell. Now in the amalgam cell, what is seen, you have mercury in both the arms, H-shaped tube, and this mercury is then having an amalgam of cadmium. Okay, cadmium, the concentration of cadmium sulfate here and cadmium sulfate here will be different. So at one place it will be 12%, and one place it will be 2.5%. So this amalgam which is there of cadmium, and above this will be cadmium sulfate solution. Now, such type of cell is a Western standard cell, which provides you a potential of 1.08 volt, and this Western standard cell is used to calibrate all your pH meters, potentiometers, wherever you need to measure the EMF. And the speciality of this particular Western standard cell is it provides you constant potential up to 99% of its lifetime. It does not happen like in your simple pencil cell, lead acid, not lead acid, that is your zinc pencil cell. If you use it in a torch, you will find that it gets discharged, and towards the end you cannot use it in the, like, if it requires more power. So almost after 90% of releasing the power, it starts getting discharged in such a way that you can't use it further. Okay, whereas up to 90%, 99% of its lifetime, it provides a constant potential. Potential doesn't drop like your pencil cells. So that is the important feature, and that's why it is used to calibrate all your potentiometers and pH meters. Okay, so that is all regarding the electrode concentration cell. Then coming to electrolyte concentration cell, you have uh, something called as cell with transference, where the transfer of ions can take place, and a cell without transference. So in a cell without transference, there will be the cell is connected back to back. You can see silver is kept here. So if you can consider this as the a whole cell, the in between will be a silver plate which separates the two compartment, and this separation, it is reversible with respect to chloride ion. On this side also you have a platinum electrode, here also platinum electrode, here you have H plus ion concentration, and here you have another H plus ion concentration. So this is something which is without transference, and this is one with transference. So you have an electrolyte concentration cell, but with transference, that is a membrane is there, semi-permeable membrane, which will allow the transfer of ions. So such two types of electrolyte concentration cell are there. Apart from the electrolyte concentration cell, you may be having two such beakers, both having copper sulfate solution, but one is 1 molar and another one is zero point 0.1 molar. So depending on that, we find that oxidation reduction reaction takes place. Okay. So potentiometric measurements are made in the absence of current flow. This is an important statement. There is no current flow when you are performing a potentiometric measurement. So the potential measured is that of the galvanic or the voltaic cell with a reference electrode as one of the half cell, and other is the indicator electrode that we all know. Okay, now coming to the electrolytic cell, like we see that the electrolytic cell drives a reaction with an applied voltage. So applied voltage is used to drive a chemical reaction inside the electrolyte. here current flows in the cell. So electrochemical cell like metallic conductors resist the flow of charge. So we see that it follows an Ohm's law where E is equal to I into R. So the unit of E or IR is termed as the ohmic drop, is the amperes into volts per ampere, so that becomes volts. So where E is the potential in voltage, volts, I is the current amperes, R is the resistance in ohms. Okay, so the current is the rate of charge flow in a circuit or solution, that is coulombs per second. So charge is C per second, and voltage, the electrical potential difference, is the potential energy that results from the separation of charges. We know wherever you have accumulation of charges, it will lead to joules per coulombs. Okay, so 1 volt potential results when 1 joule potential energy is required to separate 1 coulomb of charge. Okay. So what is the net effect of current in a cell? Now, if there is a current in a cell, then there will be an IR drop. So when there is net current in cell, the measured potential between the two electrodes is not simply the difference as calculated from the Nernst equation, E cell equal to E cathode minus E anode, but two additional phenomena. One is IR drop or ohmic drop, it is termed as ohmic drop, and polarization is considered. Now, this part is very much useful for the chemical engineering, metallurgical engineering students. Okay, so E applied is equal to E cathode minus E anode minus the ohmic potential or the IR drop minus the over voltage. Okay, now IR drop can be minimized by having very small cell resistance or by using an high ionic strength solution or by using a 3 electrode cell. And the ohmic drop here is explained as, like, if you are having, let us take an example of AgCl, chloride and cadmium, like two electrodes are taken, one is cadmium, one is silver, and it is placed in a solution which is having cadmium ion concentration 0.005, chloride ion concentration is high, that is 0.2. Okay, so you have excess of AgCl here maintained. So in such a cell, it is expected that cadmium will undergo reduction at the E naught value is minus 0.403, and silver chloride with electron gives silver and E naught is plus 0.222 volts. Now, what is seen from here? If the E naught values are seen, this will undergo oxidation, this will undergo reduction, or at this place, reduction will take place. So, E right in figure, this is the cadmium one. Is this one minus 0.403 minus 0.059 by 2 log of 1 by the concentration of cadmium ions, that is 0.005 is written here. Okay, so your E right comes out to be minus 0.471 volt, and that for the E left, we are not assigning where oxidation is taking place or reduction is taking place. We are just finding out what are the potentials of your E right and E left. So the E left potential comes out to be, this is positive 0.222 minus 0.0591 log of 0.20, that is your chloride ion concentration. Okay, so that comes out to be 0.263. So this is a positive value, this is negative value. So to have zero current condition, now we know that here it will undergo oxidation, and this will, at this place, reduction will take place because we have this negative value, right? तो अगर यहाँ पे ऑक्सीडेशन होना है बिकॉज इसका पोटेंशियल माइनस है, तो हमको अगर जीरो करंट कंडीशन चाहिए तो हमको इसको उतना पोटेंशियल अप्लाई करना पड़ेगा, so that it stops the oxidation reaction, right? So for zero current condition, if you want that there should be no current in the cell, you have to apply like how much potential should be applied here. here. Okay, so E applied will be equal to E cell value, which is equal to E right minus E left. Now if your E right is minus 0.47 volts minus the E left here shown is 0.263 volts. Okay, we are very sure that here reduction will take place and here oxidation will take place. We want to stop that reaction completely, and that's why we are doing this calculation. So what is calculated? We need to apply a voltage of this. When you calculate, it comes out to be minus 0.734 volt. So if you apply a potential of minus 0.73 volt, it is just balancing the oxidation reaction of this, and no oxidation will take place here and no reduction will take place here. Now if no reaction will take place here by applying minus 0.734 volt, then what we see that the electrode reaction, although it is placed in this electrolyte solution, it will be still, there won't be any electrochemical reaction occurring here if it is maintained that. Things are clear? So you get a zero current condition by applying this potential. Now when this is useful for understanding the corrosion control also. Now if you consider some corrosion is taking place for this particular electrode, then you can calculate in this way and you can apply a specific potential so that this electrode will not undergo oxidation and you maintain this electrode properly without undergoing any corrosion reaction. Oxidation means what? Oxidation means corrosion, right? So this is useful for understanding that also. But here we are trying to understand what is ohmic potential or IR drop. So we need to apply a potential of minus 0.73 volt to prevent passage of current and maintaining a zero current condition. Now, if you apply something more or something less than this, if you apply more than this, then the electrode reactions will be reversed. Or if you apply lesser than this, or if you apply lesser value like minus 0.6, then this will undergo slow oxidation. So E applied must be minus IR volt more negative than the thermodynamic potential of the cell. So E applied will be equal to E cell minus IR. Now you are understanding what is E cell and what is IR, E applied. Okay, so for this particular condition, you have to, depending on the analyte concentrations, we have calculated this to be minus 0.34 volt. Okay, so that is what is IR. So we need to apply voltage of 0.734 volt to prevent passage of current in, this is the figure A. Okay, now to calculate the applied potential required to develop a current of 2 milliampere. Now you want to develop a current of 2 milliampere. What is done? A known resistor of 15 ohms is connected in place of this particular cell, and now when you place a 15 ohm resistor here, then you calculate the E applied is equal to E cell minus IR. So E cell value is minus 0.734 volt minus I into R. The R is here 15 ohms and you want a current of 2 milliampere, means 2 into 10 to the power minus 3 amperes. So this comes out to be 0.03. So IR is 0.03. So if you consider this, if the resistance of your solution is this much value, then it will be little higher potential has to be applied. So minus 0.764 comes out to be the answer. So you need to apply a potential. Applied potential has to be higher than the E cell value which is coming out here. If the resistor is 15 ohm and you want a current of 2 milliampere to flow. Now, if you want a higher current to flow, like for example 5 milliampere, then if 5 milliampere current is required, you need to apply little higher current because it will be 5 into 15, because the resistor, if we equate and say that this is the resistor value, 15 ohms of this electrolyte solution, or we are using this, then this value will still increase. If this increases, this will become maybe 0.78 or so. So the moment your current goes on increasing, your E applied needs to be increased. So therefore, to maintain 2 milliampere current in the figure B, this is the figure B, the applied potential has to be minus 0.764 volt. Hence, a high ionic strength electrolyte or a special 3 electrode cell is useful in minimizing the IR drop. So, if you are having a supporting electrolyte in this, which will minimize the resistance, then you can have this increase will the IR drop can be minimized. The ohmic potential can be minimized by that. Okay, so this is what is seen if you go for this. So this is your E applied and this is the current obtained. So when you apply a current up to this minus 0.7, like this is the thermodynamic, like the theoretical value which is calculated. If you see the theoretical value will be what? This plus this, that is 6.2, right? So that will be this zero point 0.4 minus zero point 0.4 minus zero point 0.2. So you are like the thermodynamic or the literature value is at zero current, the potential is 0.73. Okay, and when you apply a little higher potential, the current value goes on increasing. The electrochemical reaction starts here, and when the electrochemical reaction starts here, that is 0.734, this is 0.734. So when the electrochemical reaction starts here, as you go on increasing the potential, the current also goes on increasing. Now what happens after some time, when the current goes on increasing, it so happens that the electrodes starts getting polarized. Now electrode starts getting polarized. I don't know whether there is a diagram there. Now you can consider this particular electrode. If this electrode is negative or this electrode is maintained negative, uh, all the ions which is present in the vicinity of this electrode are discharged at the electrode surface during this course of time, that is when you are increasing the potential gradually. Now what happens that when you increase this potential gradually within like say 5 seconds, the like you program your instrument accordingly, right? So it is changing, the potential is changing, and within 5 seconds it has changed from here to here. In 5 seconds time, the ions in the vicinity are depleted. Now the ions in the vicinity are depleted, the cations are depleted, so there are no more ions. It takes some time for the ions from the bulk of solution to approach the electrode surface, and that is why the surface of the electrode gets polarized. It is negatively charged, all the cations in the vicinity are discharged. Now what is remaining around it is only the negative ions, that is the polarization begins here. Now the polarization begins and the linearity is deviating. Now when the linearity deviates, you get some over voltage. So at 7 milliampere current, this is the over voltage. That is, you need to apply this much potential to bring about electrolysis in such a way that it will give you this current, this linear graph. So this is your E cell value. Now this is your E cell minus IR. At 2 milliampere current, the IR is this much. Okay. So the applied potential has to be this. Now at 7, I'll take first the 4 milliampere position. At 4 milliampere current, your applied voltage should be minus zero point 0.8. At For getting a 7 milliampere current, your applied potential has to be higher than this. Here you can see the applied potential has to be higher than the theoretical value of this, because you consider it has to go linear way. This is the dotted line. So we come to an important definition which is very frequently asked: define decomposition potential. So decomposition potential is the potential at which active electrolysis takes place, or you get copious evolution of gas, or um, a constant current flows through it. So theoretically, how you define it? Decomposition potential of an electrolyte is defined as minimum external voltage that must be applied in order to bring about continuous electrolysis. If applied voltage is gradually increased, there is slight or very small current until when the applied voltage reaches certain value where the current suddenly increases rapidly with increase in EMF. This potential value where continuous electrolysis begins is termed as decomposition potential. It can be theoretically calculated from Nernst equation if the electrolyte concentration and E naught of both the half cell are known. Depending on the nature of metal, see this is made bold. Depending on the nature of metal electrode and the surrounding electrolyte conditions, it is not necessary that always the actual decomposition potential will have the same value as the theoretical value. Okay, and because of this, we see that number of phenomena and electrochemical evaluations can be done. So generally, the actual decomposition potential is higher than the theoretical decomposition potential, uh, and this happens due to polarization. So theoretically calculated decomposition potential for this cell is 0.734 volt. Okay, so the decomposition should start here, but we see that it follows, you get current, but after some time, once you get certain current value, it shows deviation or it shows polarization of the electrode, and the electrode is not giving you the same current further. Okay, so your decomposition potential is the potential value beyond which you get continuous uh, electrolysis or copious evolution of gas. Okay, so that potential has to be. So after overcoming the polarization and over voltage, you get the decomposition potential. Okay, so what is polarization? Now, polarization and over voltage. So due to polarization of electrode, there is an over voltage. So polarization is the departure of electrode potential from its theoretical Nernst equation value on the passage of current. So cells that show non-linear behavior at higher current are said to be polarized, and the degree of polarization is given by over voltage or over potential, symbolized by something sort of pi sort of thing symbol. I is equal to E applied plus E cell by R, where minus E applied by R plus E cell by R is the current. So when the current is 0, minus E applied is equal to the E cell value. So a plot of E versus E applied is linear with an intercept of E cell by R and a slope of minus 1 by R. So here we see this diagram. Okay, this we have already discussed. So what we see, what is over voltage? Over voltage is the potential difference between the theoretical cell potential and the actual cell potential at a given level of current. At a given level of current means at 7 milliampere current, this is the over voltage. At 6 milliampere current, the over voltage will be from this point to this point. Okay, at 4 milliampere current, there won't be any over voltage. The theoretical decomposition potential at 4 milliampere current is the same as the um, applied potential. Okay, so theoretical and the actual potential is same and gives you same current. But as you go ahead, you will find that due to polarization, the theoretical value and the actual values are different, and the difference between the theoretical value, this is the theoretical value and this is the actual value, gives you the value of over potential, that is over voltage. So here we see that the E applied is equal to E cathode minus E anode minus IR minus the over voltage. Okay, so an over voltage of minus 0.023. This is wrongly written here. Here it should be a 0 here. Minus 0.023 volt is observed for obtaining 7 milliampere current. Writing this is very important. Obtaining 7 milliampere current. So for obtaining 4 milliampere current, there is no over voltage. That is, theoretical value is equal to the actual value. But for obtaining 7 milliampere current, there is an over voltage. The theoretical value is lesser than the actual value because of over voltage, and that is how you get the over voltage. Now in this case, what is your decomposition potential? Now you can say your decomposition potential is this value beyond which you are this you are getting the uh, constant current, linear current. Okay, so for 7 milliampere current, theoretical potential is minus 0.844 volt and the actual potential is minus 0.867 volt. Okay, so the difference of the theoretical and actual potential will give you the value of over potential. Now coming to why polarization and how. So the polarization is an electrode phenomena that may affect one or both the electrodes separately. So the factors that influence polarization is the size of electrode, shape of electrode, and composition of the electrode. What material it is made up of. Then composition of the electrolyte solution also will decide the and current level desired, then physical state of the species participating in the cell reaction. So when polarization is so large that current in the cell becomes independent of potential, it is said to be completely polarized. So in such condition, you say that this is the limiting current, onset of polarization, and this is completely polarized electrode. Many electroanalytical techniques work under the condition of complete polarization. Okay, so this is regarding polarization. Now there are different types of polarization. One is concentration polarization. Now why the electrode gets polarized? Here is the diagram. Okay, now I'll first explain to you the diagram and then we will see the definition and all. Now this is the electrode surface. Now initially when the process begins, okay, the positive ions, cations in the vicinity, like this is termed as the nonest layer, which is in almost nanometer range, and this is the bulk of solution. Now bulk is having uniformly distributed cations and anions of the electrolyte solution. So what you find here is all the cations will be discharged here and only the negative ions which are associated with this cation will be remaining here. So in the nanometer or Armstrong range here it is shown, you will find that there are only negative ions remaining. The electrode is also negatively charged. So you get the electrode gets polarized because there are all negative ions around it. The positive ions from this should migrate due to concentration gradient, but that process of mass transfer or this ion transfer is little bit slower. Okay, so when you start this electrolysis and you go on increasing the potential, you will find that a time reaches that it gets polarized and all negative ions only are there in this particular nanost layer. This diffusion layer or the nanost layer, only negative ions remain. And because of this, your electrode is getting concentration polarized. So that is the meaning of concentration polarization. So concentration polarization is due to limited rate of mass transport from the bulk of the solution to the surface of electrode. The rate at which reactants are consumed in the diffusion layer is more than they are brought from the bulk of the solution to the electrode surface. The diffusion layer becomes relatively depleted in the reactants and the transfer of electrons at the electrode surface can't be faster than the rate at which reactants are brought to the electrode surface. So polarization can also occur when the rate at which products are removed from the surface is less than the rate at which they are produced. Okay, so this is diffusion. So diffusion is the movement of ions due to concentration gradient. Okay, and a net movement occurs because species move from region of higher concentration to a region of lower concentration. So from the bulk, it should come first to the diffusion layer, and then it will be discharged or at the electrode surface. So once equilibrium is reached, no net movement occurs, although species continue to move. For a reactant approaching a surface, net rate of diffusion is equal to K into bulk concentration minus the surface concentration of that particular analyte. So where K is the rate constant. So, so there are three important steps occurring. One is migration, one is convection, and the other one is diffusion. So diffusion is due to concentration gradient, and migration is due to the potential applied. The migration of ions take place due to the electrical field movement of ions through the solution by electrostatic attraction to the charged electrode. And convection is if you are stirring the solution, due to stirring action the movement of ions take place. But it is seen that this layer, if it is in Armstrong, the Nernst diffusion layer of stagnant solution, this, although you stir the thing, this layer is almost stagnant unless and until it is diffusing through this. Okay, so migration is the phenomena where the ions move due to the electric field, and convection is movement due to mechanical forces such as stirring or shaking. Note that the concentration polarization can either be desirable or undesirable depending upon the application. So it is not that concentration polar. In corrosion studies, if the electrode gets polarized, due to polarization, over voltage increases. If the over voltage increases, means the electrode reaction stops. So we want to stop the electrode reaction or the surface reaction. So in corrosion, we see that polarization and over voltage are useful. Okay, then next one is kinetic polarization. So what is kinetic polarization? In kinetic polarization, gas formation takes place at the electrode surface. Okay, kinetic polarization occurs at the electrode that yield gaseous products because kinetics of gas evolution process are slow and complicated, and therefore due to formation of gas, a thermodynamically favored reaction need to be fast. So an over potential may be required to overcome an activation barrier of large delta G. So kinetic polarization can be negligible for decomposition or dissolution of metals like copper, silver, zinc, cadmium, and mercury. It is significant for reactions involving transition metals such as iron, chromium, nickel, and cobalt. For example, reactions involving gas evolution such as H2 production or O2 production, the over potentials are as large as 1 volt are also seen. Okay, so so this is the important part, most important part. What is over voltage? Over voltage is the potential difference between theoretical cell potential and the actual cell potential at a given level of current. So it has been experimentally found that the decomposition voltage of an electrolyte varies with the nature of electrodes employed for electrolysis and is in many cases considerably higher than that calculated from the difference of reversible electrode potentials. This excess voltage over the calculated back EMF is known as over voltage or over potential. So over voltage may vary independently for cathode and anode. Hence decomposition potential is given as ED equal to E naught cathode plus over voltage at cathode minus E naught anode plus over voltage at anode. Okay, so over voltage at cathode and anode depends on nature and physical state of metal employed as electrode, current density, temperature, physical state of substance deposited or formed as a product of half cell reaction, then concentration gradient and the presence of inhibitors. Okay. Then there are certain depolarizers are also used. A depolarizer is a species that is easily reduced or oxidized. It
Previous
helps to
slide,
maintain
please.
previous one. This
Yes.
these two are important: over voltage and the decomposition potential slide. Now, decomposition potential is the potential when
Ma'am,
active electrolysis takes
ma'am,
place.
ma'am, we
Yes.
have class now.
Okay, yeah, this is almost done. I'll give you the book PDF also because in the book it is given in short. So depolarizer will react in such a way that it will remove the polarized part and help in the faster electrode kinetics. Okay. So compounds like hydrazine, nitrate ions, and hydroxylamine act as cathode depolarizer. But in corrosion studies, you don't need a depolarizer. You want the metal should get polarized so that corrosion reaction will stop. The nature of electrode, nature of environment, and the nature of product formed at the electrode electrolyte interface plays a pivotal role in predicting whether the electrochemical reaction or the corrosion reaction will proceed further or not. So to understand this, you should know what is polarization, what is over voltage, what is decomposition potential. Okay, so decomposition potential is one which is theoretically calculated from the electrochemical series, right? So at different level of current, you have different level of decomposition potential. So at zero current, the decomposition potential is this. At 2 milliampere current, the decomposition potential can be said like this, or so on. So a time reaches that the decomposition potential is not at all the same as the theoretically calculated one, but this is the actual potential. So the difference between these two values is termed as over potential. Things are clear, and I have tried to explain you the most complicated part of this in the simplest language. The books that you can refer, I'll give you book PDF of Tara. Then you can go through Gen and Gen, or you can go to this particular analytical chemistry by Skoog and West. Okay, so this is a little higher level book. You can read the thing from these two books. Okay, so with this electrochemistry part gets over. In the next class, we will start with corrosion. Okay.